instruction, we list all the tools and fixtures, what MNTE they need, all the process materials, and we just go through the actual process of them having to do it. Most of the work happens within the software, so we've tried to subtract a lot of the operator interaction out of it. But we have it there so that we can officially train them, sign them off, and then they can do it, and we can run metrics on it and the whole bit that Lucas will get into later. So that's the procedure. The calculations, I'm not going to get into this kind of a night right here, but I'll skip some of the formula stuff in the middle. But the big thing that we look for, how do you turn this on?
Push the button.
Okay. So the big thing that we look for here is the form of the sphere. This is the 3D, the 24 points. The form is just simple, the maximum minus the minimum. You can get the form, and that kind of tells you the overall health of your machine, the CMM. We do the same thing for the scanning. When we're coming around and scanning that on the 4 loops, again, the form max minus the min, that can tell us, how well we're scanning. Squareness is this messy stuff here, but obviously we get 3 squareness, XY squareness, YZ, XZ, and those are geometric errors, and those are kind of inherent to CMMs. They happen, and you can just kind of watch them because they can drift. The other ones, X linear, Y linear, Z we can't get, and then the spatials are all corner to corner. So we get 4 of those, and these all tie back to the ISO 10360 that Mario was talking about earlier. That's a direct tie back to the standard. So we can get those pretty quickly, a rough estimate. The other thing we kind of watch, average radius. That is kind of a health check on the gauge itself, the machine checking gauge. So if we notice that the radius changes all of a sudden, we know that maybe the inspectors dropped it, and it's not going to shrink, it's not going to grow. So we just kind of watch that so we can monitor the health of our gauge. The pivot location, so what we do there, before we start gathering data, they're at the center, that center kinematic post. We measure that post, and we build our coordinate system right there, and we create an origin. And then we come off and we measure the whole sphere. After we pull that arm off, we go check that origin again. So if it doesn't repeat within that B89 number, we know that something moved, that data is suspect, so they have to rerun it. The last 2 things, temperature, obviously, that like Mario said earlier, large influencing factor, variable, and then the Z number, we try to keep track of who's running it, things like that. So those are some of the things that we try to watch. Then, obviously, for the data that's coming back, after we had all the 20 runs, on all of those different forms, scanning, we ran, basically all our Gaussian stuff, standard deviations, skewness, kurtosis, and then all our box plot stuff of, Q1, Q3, and max min. Just kind of do that for kind of everything. Another thing that we did with this project, we ran a GRNR. We had 2 inspectors with 12 parts, 7 trials. The numbers came back with a bulk of the coming back in equipment. Very little coming back with inspector. And like I mentioned earlier, we really tried to subtract a lot of that out. We built everything into the program, so that was really good. I'll leave it at that. You wanna say anything else?
That part-to-part variation, it's rather large. That's just telling us that if we were actually running this on, say, an actual measured part, that means that the manufacturing process of them machining those parts is off. They have to go back to the manufacturing process. It's not inherent in our machine. It's inherent in the actual machine of the part itself. So the lower that number gets, the part-to-part variation, the better the manufacturing process, but the worse our machine is. The higher that is, the better our machine is, the worse the manufacturing process. So you guys got to kind